Hey everybody, Dr. P here. This week in class, I got a lot of questions, and I mean a lot of questions, about gradients, directional derivatives, and how those two are connected and play off of each other. So instead of answering individual questions this week, I thought the best thing for me to do would be to post a video on the 4 things to know about the gradient. So if you know these 4 things, you'll know pretty much everything that is important to know about the gradient of a function. And to do this, I've put up an example, f of xy equals x squared plus y squared. I could have used something much more exotic, but I thought that a familiar function would be best for talking about the different things that we need to know about the gradient. I've also put up several different representations of the function. Here's the formula, here's the contour diagram, and here's the graph. As always, the graph is a paraboloid for this function. And I've also put up a specific point, p equals ab, which we're going to let be the point 1, negative 2. Notice that's a point in the plane. It's not a point in 3-dimensional space. So I've marked it here in the xy plane, and here it's meant to be in the xy plane as well, although it's not easy to tell from the picture. And the corresponding point on the surface is somewhere above point P. It's going to be at 1, negative 2, and then the value of this function at that point, which is 1 plus 4, or 5. Okay, the first thing to know about the gradient of a function is how it's defined. So let's write down the definition of the gradient of a function. If I have a function of 2 variables that is differentiable, I can define its gradient at a point AB to be the partial with respect to x of f at AB times I plus the partial with respect to y at AB times j. A little bit about the notation here. I'm doing something that is probably unusual that your instructor may not do, which is I put a vector sign over this symbol, which is nabla f. Your instructors may not do this, but I like doing it because it reminds me that the gradient is always a vector. So you'll always see me put the vector sign over nabla f, and you even see that in my problem sets. You'll also notice that I'm evaluating this at a specific point, AB, because you can write down what the gradient is in general, but really we usually talk about the gradient at a specific point or some other point. So here's the general definition. In this case, I know that f sub x at AB is equal to 2a. That is, the partial with respect to x is 2x, and I'm putting in the x coordinate. Actually, let me write that down first. So f sub x at x comma y is 2x, and f sub y at x comma y is 2y. So in this case, the gradient of f at AB would be 2 times the x coordinate, that is 2a, times I, plus 2 times the y coordinate, that is 2b, times j. And for the specific point that I put up, for point P, I can write down that the gradient of f at P is 2 times a, which is 1, so 2i, 2 times 1, plus 2 times b, or 2 times negative 2j, so let's make that a minus 4j. That's the gradient of f at this specific point that I've written down here. All right, so I'm going to record that over here so I have access to it at all times. 2i minus 4j. Now, something to notice about that, that is a vector that lies in the 2-dimensional plane. It is not a vector in free space, which means it would not be reasonable to expect this to be tangent to the surface. That is, if I look at this point here, remember that's the point on the surface, this little blue point is the point on the surface corresponding to x equals 1, y equals negative 2. If I draw this vector, it's going to be parallel to the xy plane from this point. So it's going to look something like it's going to go 2 units out this way, and then 4 units over this way. It's going to point somewhere in this direction towards the window. I know you're not in my office, so you can't see there's a window over there, but there is one. Okay? But it's going to point straight out. It's not going to be normal to the graph. It's not going to be tangent to the graph. It's not going to be tangent to a tangent plane. It won't lie in the tangent plane. It's just something in the horizontal plane. Okay, you have heard something about gradient vectors being normal to level surfaces of a function of 3 variables, but that is a separate topic from this. Okay, so just keep in mind gradient's a vector, and for a function of 2 variables, the gradient is a vector that lies in the xy plane. I actually could draw it over here if I wanted to. But we'll get back to that later. Okay, so that's the first thing to know about the gradient is how it's defined. It's defined to be the partial with respect to x at a point times I plus the partial with respect to y at the same point times j. And then if you have a function of 3 variables, we'll tack on the partial with respect to z times k. Now, the question that you should be asking yourself at this point is, why in the world would we want to take partial derivatives and turn them into a function? Or, sorry, not a function, into a vector. Why would we want to take partials and turn them into a vector? That's a good question. And the answer right now is not going to be all that satisfying. The answer is because it ends up doing a lot of cool stuff. And we're going to show why the gradient does that cool stuff when we turn it into a vector. But first, let's talk about directional derivatives. I hate having so little board space to work with. I'm going to have to use some abbreviations here, I think. We're going to talk about directional derivatives. So I'm going to take my point P that I've already selected, and I'm going to choose a direction from that point. So let's say I want to find the rate of change in the direction, or let's say rate of change at P in the direction negative 3i plus j. And I'm just going to do a quick check and make sure that text is visible there. It is barely, so I'm going to live with this. Okay. So I want to see what the rate of change of the function is at P in the direction negative 3i plus j. All right, so in my picture, that direction is going to look like this. I'm going to guess at exactly what direction that is, but it's going to go to the left quite a bit and up just a little bit. Okay, now just from looking at the contour diagram, I can make some guesses about what the directional derivative is going to look like, because the directional derivative is just telling me the rate of change of the function if I start at point P and walk gradually in this direction. Well, I know that this is on one of the outer contours, and for this graph, outer contours are going to be at greater heights, which means that as I walk this way, I'm moving towards these inner contours, which are lower, and then eventually I go out again, and the contours get higher again. But remember, directional derivative just measures what's happening near this point as I start moving in this direction, which means initially I'm getting lower, and I should expect the directional derivative to be negative. So my guess is that it'll be negative. But let's see if we can make a numerical guess about what the directional derivative is going to be. Now, in order to do this, I'm going to make a guess about what the function value is going to be if I actually travel the entire vector negative 3i plus j. And to do this, I'm actually going to use linear approximation. I mean, I could figure out from the function formula what's going to happen to the function after I travel the vector negative 3i plus j. But in order to see how the derivatives work here, we're going to use linear approximation. And this part's a little bit delicate, so I'm going to start a new video for this. So this is the end of the first video. Look out for the second one.